So let's move on and let me introduce our speaker today. Rod Robinson is the Principal Research Scientist for the National Physical Laboratory. Welcome, Rod. Can you tell us a little bit about your talk today?
Yes, Roger. So I'm going to be covering some of the sort of requirements and needs for specifying your measurement needs and the uncertainties and capabilities of your measurements. And I'm going to focus on monitoring and measuring methane.
Excellent. And a particularly hot topic at the moment. So, Rod, are you ready?
I am indeed. So
carry on, your 20 minutes start now.
Okay, thank you, Roger. So as Roger said, I'm a Principal Research Scientist in the Emissions and Atmospheric Metrology Group at NPL. In overview, I'm going to cover what we're putting together as a kind of basis for defining your measurement needs, the metrology and data quality statement. I'm going to look a little bit of background on methane measurement technologies and why we measure methane. And then I'm going to give some examples of validation and performance testing that we've done and look at sort of standardization into the future. For those of you who are not aware, the National Physical Laboratory, we are the UK's National Measurement Institute. We're owned by BEIS. We have some partnering with other universities, but we basically look after the national measurement system, which provides the basis for fundamental measurement in the UK. And our primary goal is supporting UK industry and UK in measurement science. The Emissions Atmospheric Metrology Group that I work in, we're a bit more sort of outward and industry focused. And so we cover emissions to air, and we cover everything from the development and support the development of new technologies and new methods. We have a range of facilities that let us do validation and testing of measurement technologies. And we actually offer commercial services to industry as well, both in the ducted point source emissions and also diffuse and fugitive emissions. I cover and head up the emissions area, and then also we cover atmospheric composition measurements. So we are putting together this concept of really specifying up front the metrology, the measurement quality in a project. And we're proposing this is done at project development. And what we're trying to pull together is a formal and consistent way of dealing with this sort of measurement quality. And that's to define specifically what your objectives are, what the purpose of the measurements are, but also what the output is that you require from that. And therefore what the data quality objectives are on any measurements or monitoring that you do. And that's really to make sure that all measurements are really fit the purpose. And then really playing to our sort of strengths in terms of looking at the traceability, the comparability of measurements, really to make sure that all of the data outputs are usable and that you fully understand and can compare them with other technologies and other projects. And really to address what standards and good practice are in place, and also importantly, what other metadata should be caught during the project to really make the interpretation of data so that you can actually make use of those data going forward. For example, ensuring that you have all of the plant operating condition data recorded alongside any emissions monitoring data to be able to fully interpret the results. And then a whole range of data quality sort of requirements in terms of how data are handled, the security, storage, etc. So we're looking at defining a sort of common approach that's used within research programs, etc., in order to define up front some of these aspects. And really just to reinforce why we think these are important, it really supports the outputs from projects to ensure that the results and conclusions drawn are robust, sensible, but also to really get the most out of data to make sure that it is available, can be used potentially for other uses going forward, to ensure that data from different projects is comparable, as I say. And without those, then clearly you can spend a lot of money and time and resources in measurements and monitoring and in technologies that may not actually deliver the answers or the conclusion that you were expecting. You may get inconclusive results or be unable to make the decisions that you'd hoped you'd be able to make. And so what we're looking at really is defining, and we're working with some of the big innovation programs to try and come up with a common way of defining these aspects to projects. And we're starting to look at how you might, for example, if you're assessing new technologies, come up with common ways of doing it, such that assessments carried out in different projects can be compared. So I said in this talk, I'm going to focus on methane and methane measurement. I mean, I think clearly, as Roger said, everyone is aware of the importance of methane. It's a strong greenhouse gas. It's currently a very high priority, particularly looking at the emissions of methane, fossil methane from industrial activities. And there are a lot of international programs that are going on at the moment. And I think there's increasingly a focus, I mean, we've seen from the recently published EU methane strategy, increasing focus on industry addressing and reporting and reducing the emissions. And this is leading to more requirements on ensuring that those measurements are traceable, are comparable, that you have, that as an industry, sort of can place confidence in the results that you're reporting. Fundamentally, it is just a measurement problem, but sometimes what is being required to be reported, for example, methane mass emissions, isn't necessarily what is directly measured by sensors. And so really understanding that whole measurement problem is the issue. I think it's also important to really clearly define your measurement needs, because you want to be led by your requirements and not be pushed by technology. And when we look at methane, then there are a whole range of different technologies and methods for measuring methane, and there are a whole range of different reasons to measure it. So I won't go in detail through all of these, but I think the range of point sensing, low cost and mid cost sensors, through the more typical sort of LEL type safety sensors, things like catalytic sensors, and then optical sensors, which can be very specific to methane and can range from the portable handheld sensors to large systems, open path systems, and even satellite measurements. And if we look at the reason for measurements and the types of measurements that are made, then clearly there's a long history of doing safety measurement, but also we have the leak detection types, of the bottom-up detection and sensing of individual leaks from components. And then we have the kind of more top-down, looking at areas of sites or looking at regions. And then we have the real top-down satellite sort of finding hotspots. And then we're moving more towards the ability to put in place monitoring, which is continuous, so you can continually screen and report emissions from sites. And one thing we did do at MPL with BEIS was develop a kind of taxonomy to describe both measurement requirements in terms of spatial, temporal, limits of detection, data quality. So a way of describing in a common way what your measurement needs are, and a way of describing measurement techniques, so you can do a mapping and understand what techniques are appropriate for what requirements. And I think it's also important to bear in mind that often what you want to report is methane is not just the methane concentration or the identification of leaks, but also the mass emission rates. And that is clearly a step further in data, in the data calculation. It's a derived, usually a derived measurement from concentration and other parameters in order to determine a mass emission rate. And there are a number of different ways that is done. And these introduce, again, uncertainties and should be an aspect of the data quality. And really, in terms of with techniques, what I wanted to stress was that with validation, it's not just the assessment of the performance of the sensor, but it's also the assessment and performance of the methods and the protocols. So it's not just technique validation, it's also the validation of the methods that are used to turn those sensor data into reported figures. And I think we're now seeing, we're moving from research projects. There are a lot of technologies and techniques have been developed in the research environment, in the research community, and we're moving now towards needing techniques and methods which can be deployed at scale, can be deployed in a cost-effective way to deliver data for industry. And I think that's the point where we really need to have and start to move towards standardized methods, towards validated methods, such that industry and the regulators can have confidence in the results. So I was going to really give some examples of some of the validation work that we've done, and really cover different aspects of validation and testing through looking at the performance specifications of technologies, validation of technologies, and then moving more towards some of the technique validation and standardization activities. So I'll cover a little bit on optical gas imaging, a little bit on some sensor validation, look at more general fugitive emission techniques, and just cover some work we're doing looking at satellites as well. And I should say most of the work that we've done has dealt with onshore applications, but the principles apply offshore, although of course there are significant additional issues that would need to be addressed in validating and proving technologies for offshore use. So if we look at optical gas imaging, I suspect many of you will be familiar with these infrared cameras, their widespread use across the gas industry and oil and gas in terms of being used to detect and visualize leaks. They don't give a quantified result. They give you a visual indication of a leak, although suppliers are now starting to offer both concentration and emission rate products. But these are an early stage. There are very few standardized protocols for the use of these technologies. There's some guidance produced, and the first kind of performance spec, which has come out of the US EPA with their Quad OA performance spec. But there's very little in the way of standardized performance and standardized methods for using these cameras. And I think it's generally understood that there's quite a degree of operator can be quite subjective in the use of these cameras, and they're influenced by a number of things in the field. So we at MPL developed a capability to validate cameras against this Quad OA guideline. And one of the issues with the Quad OA performance spec is it's quite open to interpretation in the way it's written. And we did a lot of work and went back to the US EPA to define what that specification actually meant. Because when you follow the exact specification, then the emission rate you need and the releases you need to test the camera are actually quite high and not possible just to do in a lab environment. So we used a controlled release system that we developed to deliver the test specifications that are in the Quad OA performance spec. And we've done testing with a number of camera operators in terms of assessing their equipment against that standard. I think it's worth bearing in mind that there are now quite a number of different suppliers of infrared optical gas imaging cameras. I think some of the things that we understood and have come to learn from doing those tests is that there are quite a lot of operator dependent factors in the use of the cameras. As you would expect, the cameras become less sensitive the further away you are from the source. But also there are some kind of operator dependent things that it's easier to spot plumes and sources when they're moving. So in some cases, you might expect with high wind speeds, you get more dilution. It's harder to see the emission, but also with very still conditions, you get less movement and it's hard to see the plume. So and one of the issues with the testing specification is that it merely says the camera operator should be able to discern a plume. There is no absolute sort of traceable numerical way of defining whether something is visible or not. And so we've tried to develop an approach in terms of the testing that lets us have a more objective way of doing that. I think that's another issue when you start to develop performance tests, is that they should then be reproducible by different test facilities, by different test houses, to be able to test in a way which is consistent. And I think it's also important that the test conditions are relevant to the real world. Without bringing up things like the Volkswagen issues, but the test conditions need to be representative of the kind of conditions in the real world. And the little picture there is something we're developing, which is more of a test rig based on actual equipment, so that we can produce real world conditions, and then not only address camera performance, but also start to put together some operator proficiency testing schemes as well. So one of the other bits of equipment that we've looked at is the HIFO sampler. This is used a lot in the gas industry, and it provides a means to quantify individual leaks. If you're not familiar with this system, it's basically a large air mover with a gas concentration measurement system on the back. And so by sucking the whole of a leak into the system, knowing the flow rate and the concentration, you can determine the emission rate. So it's a kind of virtual bagging. It became a bit of a de facto standard in the gas industry, but there is no formal standard. There's no independent certification of this kit. And it's been used in a lot of the early science studies that were done on the onshore gas production in the US, particularly the shale gas studies. And there were issues raised with this sampler in the literature. And so we undertook a very detailed assessment of the performance of the system in the laboratory, and also used our controlled release system to test its performance at quantifying leaks in the field. And we identified a number of issues, some of them operator dependent in the way that you run the system, some related to a switchover of the sensors within the system that can lead to some errors. We've published those, and we also included some guidance then to users on how you can avoid those issues. But I think it was just interesting that that instrument had never really been fully sort of assessed in a kind of objective way. So moving on, we're involved in the development of a standard, which is a European standard. It's actually to address the diffuse and fugitive emissions of VOCs under the refining BREF, but it's also applicable in the way that it's set up to methane. And it basically is a toolkit of technologies, a toolkit of methods, differential absorption LiDAR, solar occultation flux, the optical gas imaging, and tracer and reverse dispersion models. And they basically form different ways of measuring basically at facility scale. So these are technologies which can monitor emissions at site and at sub-site, at kind of areas of a site, and give mass emission rate quantification, and then also leak detection or leak source identification through the use of the optical gas imaging. And the standard gives a way to use these techniques together. And as a part of the standard development, we validated the standard. And this was done in using controlled release and also in real world testing. And it was interesting that the optical gas imaging system, the leaks that we found on the real world site, most of them would not have been found through normal leak detection programs. And so, as I said, we've developed a number of capabilities of MPL to allow us to test and validate methods, including a controlled release system that can replicate emission scenarios. And we have validated things like our differential absorption LiDAR, which is an optical radar system that allows you to basically quantify plumes and visualize plumes. And that the MPL dial has become something that we use then as a reference technique to validate other emission techniques. So when we look at the suite of ways you can validate technologies, using some of the high spec sort of almost gold standard techniques can then be used to validate lower cost technologies. And currently we have a number of programs underway looking at some of the new advanced sort of optical imaging and optical open path techniques, and we're doing some validation on some of the newer technologies that are coming along. And one area where we are looking at doing some validation, and this is a growing area, is in validating the UAV. So some of the unmanned aerial vehicle monitoring. There's a lot of research groups starting to use these, and in this case, it's one of the big issues is in the the conversion of the composition, the concentration measurements that are made with sensors on board the UAVs to then try and determine both the plume map and the emission rates. So in this case, we did some work with the University of Manchester looking at validating or assessing the approach they were using to fly through a plume, and then to derive the emission rates from that. And so we had known and traceable emission rates that we could release, that they could try and measure. And we've also been looking at, with UAVs, some of the issues you have in mounting sensors on a UAV, because clearly if you have a UAV sensor, the UAV itself will be disrupting the plume with its rotors and the airflow. And so we've been looking at developing some guidance on how you approach monitoring using a UAV. And then the final validation work that we're looking at, that I'm going to cover, is we're doing some work with ESA on a feasibility study to use a ground source, in this case a landfill, as a controlled release, or as a well characterized and traceable release in order to assess the performance of satellites. And the reason here is that you can do controlled releases, but a lot of the satellites, and then we're now starting to see satellites like Greenhouse Gas Sat's new IRIS, which was launched just last month. That system is able to see methane plumes from individual facilities and sites. And the issue is, if you use a controlled release to try and validate that, you've got to match that up to the satellite overpass. You see, you've got to basically have a system on standby all the time. What we looked at is, can we take a source which is emitting the whole time, an always on emission source like a landfill, but characterize that by putting in place both monitoring with our dial to understand the emission plumes from the landfill and quantify them, and then put in place continuous monitoring so that you can have a ground source which you know the emission rate at any given time. So when a satellite flies by, it can do a comparison against the emission rate. And that's a project that we have ongoing at the moment. And so just to conclude, I've really just wanted to run through there a whole set of different technologies and validation approaches that we've had, just to give a picture of how you can go about validating different techniques. Really just to reiterate that having at the beginning of research projects an understanding of what the quality statement is, what your objective is, what you're trying to monitor, and then you can assess the performance against your requirements, and then show some of the tools that are in place and some of the mechanisms you have for assessing the performance of technologies through controlled sort of laboratory testing, through controlled releases and known sources, and then comparison against reference methods. And so that really was a flying summary of some of the work that we've been doing on this in this area. So thank you.
A flying summary indeed, and even some drones thrown in there, Rod, which
indeed
OGTT have done a fair bit of work on. So maybe that'll be some of the questions that we get to. So thank you very much for that presentation. Clearly a lot of work going on in this space, and a lot of opportunities. So if I can ask the audience, if you get ready for the questions, I see some of them coming in there. Maybe I'll just kick off with one there. In that the second from last slide, that's a great big truck mounted unit you've got there. It can be difficult to get that into the offshore environment, but is that just the test unit, or how close are you to getting things to an extent that we could be looking at potentially offshore field trials?
Yeah, so with the dial capability, that's basically a mobile laboratory. It's mounted, as you say, in a large truck. The actual measurement element of that, we've got a sort of prototype design of putting that into more of a sort of turret-based system, which could potentially go offshore. But the technology at the moment is pretty much for onshore. Okay. But yes, it's something we've looked at. As I said at the beginning, offshore is a challenge.
Thanks very much for that. Pamela, I'm just going to come to you. I'm going to allow you to talk if you would like to ask your question, please.
Fantastic. Thank you so much for that very engaging presentation. I've thoroughly enjoyed it because obviously having a previously similar backgrounds to looking at quantification of measurement techniques in academia. So this is very interesting to me. Now that I'm more working in the decommissioning space, and we've recently undertaken a sort of desktop review of decommissioning emissions at the National Decommissioning Centre. We also have a PhD looking at emissions related to decommissioning activities. But the challenge here is finding data on emissions from the decommissioning, previously undertaken decommissioning activities. And that is because there are no specific criteria on how to undertake these measurements. Now, you talk about validating performance of your techniques and ensuring that it's based on real world scenarios. Now, decommissioning is a relatively new activity with different people undertaking decommissioning in different ways. You talk about site type measurement of emissions, but in the decommissioning space, I think we're looking at more at asset level rather than site stuff. So do you have sensors that might be specifically applicable in the oil and gas space or in decommissioning arena? And also where we have equipment that are, some are old and integrated with new equipment, how can we effectively validate emissions from such integrated sort of structures effectively?
Yeah, no, thank you. I think there are a couple of things to say there. So I think in a simplistic sense, then the technologies and some of the methods and methodologies that have been developed are applicable to decommissioning an asset. I think the same issue applies in terms of transferring some of these technologies to the offshore arena. But I think one of the interesting things potentially with decommissioning, and I don't know a great deal about it, would be that the emissions, I suspect, would be quite variable and potentially sort of vary in time with the activities that are being undertaken. And in that respect, I think the ability to have monitoring systems that can be screening or can be providing data in a sort of time series will be, I suspect, important. And I think that's something that's being recognized in generally in the production side as well, is we have a lot of techniques and a lot of methods which are campaign based, that you can go and get a very good understanding for your emissions at a given point in time. But I think there is a move now towards developing and looking at methods that will be able to provide continuous data. I think some of that will be useful in the decommissioning side. And I guess the other thing is absolutely, until we can get an understanding of what the likely emissions are and what the range of emission scenarios are, it's then you probably need some of the work to understand what the emissions are, which would be sort of quite intensive monitoring, to then understand, well, what is necessary in a more routine sense? What are the types of emissions you need to address, and what would be appropriate technologies to monitor them? Roger, you're on mute.
There you go, schoolboy error. Thank you, Rod. Thank you for that, Pamela. I hope that's answered your question. Please keep the questions coming. I guess, Rod, just picking up on the 5G element that you're talking about there. I mean, is that going to help us to develop, or is that a key technology for developing almost, if we were to try and get to the live TV monitoring of emissions across sites, and how far away do you think we are from being able to achieve that?
Yeah, I mean, I think what we've got at the moment are technologies which, on a relatively simple onshore site, then we can get continuous monitoring. You start to bring in play some of the issues of complex structures, vertical extent, very compact, and maybe offshore where you can't stand off and put in place sort of monitoring systems around a boundary fence and expect to capture the emissions that are coming off, then I think there are some more significant challenges. Certainly we're starting to see some of the cameras moving towards being able to do sort of continuous screening and provide an indication of emission rates, but there's still some work to do there, I would say, in terms of those algorithms particularly.
And is there, going back to, I put it in chat earlier on as you were going through, is there any guidance at the moment on the competence of the operators of these optical gas cameras? Because I think they're quite common in offshore platforms now that they're used for, you know, basic leak detection. But is there any standard on the competence assessment part here? It just seems to be maybe I'm wrong, but it feels like it's a little bit down to individual companies.
And that's actually one of the slides I flashed past, was we were actually putting together a rig that will form the basis of basically a proficiency testing scheme, so that we would be able to have operators send their teams and do some kind of training / ongoing competency test, because really it is very, very operator dependent. We saw that in the European standard validation, that the difference between teams who had a lot of experience versus one of us, you know, just for fun, picked up the camera and had a go. And there's a big difference in terms of what you can see, particularly when you're trying to spot leaks which are comparable to the kind of leaks you would spot with a sniffer, with a classic LDAR. Then of course you've got the whole methodology approach of, if you're going to use cameras to replace LDAR, do you actually go with the fact that the cameras will pick up the big leaks, and that's probably 95% of your actual emission from the site, but it may be only 5% of the actual leaking components. So there's some discussion around, if you're going to try and regulate and find leaks, you know, the cameras will do a very good job of finding the big ones. And is that then sufficient? That's the kind of way that the US has gone with its smart LDAR.
Okay. And I guess there's an obvious extension to this with the use of AI technology in the future to, if a person can interpret this, surely we can teach a machine. Is there any work going on in that space at the moment, or are we just?
Yeah, so there's a few vendors have put in place sort of like post capture software that you can add as add-ons onto these systems that will then do both plume identification for leak detection and quantification. And we've done some early sort of validation of those, and if you know how they work, you can work out how they might fail. So that, you know, a lot of them need to be set up. You know, you need to kind of configure them and set them up. So looking at a particular leak. So I think it's evolving. We're getting there, but I think those are relatively early, sort of early stage.
And are you seeing, is that vendor led or is that academic led at the moment? Are you getting a mixture of?
I think it's a mixture, but there's a lot of vendors who are adding this onto their cameras now. So these are commercial offerings. So you can go and buy these systems now.
Okay. I'll just Jeff, I'm just going to come to you in a moment and unmute you so you can ask your question, which is in a slightly different direction. Jeff, over to you. You can.
Yeah, thanks, Roger, and thanks for a great talk. A bit of a different one, I guess, but how can you measure emissions and releases in the subsea environment? Is that the same technology, or is it something completely different, way off?
Yeah, so not my area. So if we're looking aside from sort of gas detection above the surface, which is unlikely given the kind of the dispersion you'd get, you'd probably have to have a very big release to be able to, if you were going to spot it above surface. So under the sort of subsea detection, then there are technologies which some of my colleagues at NPL have been looking into, which use things like acoustic detection to pick up bubble sort of formation on the seabed. I think we also looked at whether you could potentially pick things up through sort of pH change and things like that. But I think the acoustic techniques are probably the most the most sort of likely.
Yeah. Okay. So yeah, capturing the data in a slightly different way, but could be possible, I guess.
Yeah.
Cool. I've got a second question, I guess, building on Roger's question about the AI side of things. So if you're capturing all this data, have you or could you link this to like a live model or a dynamic model of an asset, be it onshore or offshore, to actually show a live representation of what's happening in terms of where emissions are coming from and what's happening?
Yeah, and I think that really is the way that a lot of both vendors and some of the things that we're looking at is going, is really once we're now looking at the ability to instrument up sort of assets or sites to then be able to give real-time information, or at least relatively frequent updates. So we've done some work looking at distributed sampling and combining that with models to give indications and updated sort of probability map across the site of where the leak is. I know there are a lot of vendor solutions that are coming along that are looking at similar approaches, and then the integration of sensing into plant control systems and plant operation systems, so you have that full sort of linkage. I think that's really the way things are going. But from my side, the really interesting point then is, how do you validate that? How do you test that? How do you check that these things are going to give reliable data? And that's what I'm interested in, is how do we bring in place some standards for that kind of technology? If you think around some of the earlier sort of approaches when you're looking at things like safety systems, the last thing you want are sort of significantly frequent false positives, because then you lose any kind of confidence in the system. So I think there's a real need to look at how complex data transformation sort of systems and algorithms can be validated and tested.
Maybe just a question from me on the data sharing point of it. We, as an industry in oil and gas, are not very good at sharing data. Sometimes is probably the polite way to put it. But what kind of problems are you seeing in this space? Because I guess this is the detection and the things you're finding. Are we really ready to be honest about what we find? Are you getting any pushback in those areas?
I mean, yeah. I mean, let's at one level, that's an industry. That's an industry discussion. I think from my side, the important thing is that the data that you do have, and any data that you do either need to make public through reporting, or that you choose to make public through collaborative research, that you understand the quality of those data, and that data from different sources have a known level of quality and can be compared. So I think it's more about making sure and giving you as an industry the tools such that you can understand your data and understand, if you like, the metadata that goes with those, the quality statement that would go with those data, so you could have confidence in sharing them if you wanted to.
So maybe just one final question from me, just to wrap up then. With the OGTC working with the NPL, what's your ask of our industry? How can we help you?
I think the first thing is come and talk to us. Let's understand what the problems are. I thought Pamela's question was very interesting, and it would be really interesting to understand, well, what are the measurement needs? What are the blocks that you have? Where can we help and support? And also, if there are things like, if you have programs, or you have the development of things like guidance, then what can we support in the way of metrology, adding in the sort of the identification of the measurement issues, or some of these quality issues? How can we support you in addressing those?
I think there's potentially a follow-up there with Pamela, and I see Willie Reed's on the call as well. I think there's a follow-up with academia here to see what we can jointly start working on with you. So Rod, thank you very much for your presentation. Fascinating session today. So just leaves me to close the event. That's our 40 minutes up, and Rod, thanks very much, and hope you now have a nice relaxing weekend after that. There's a QR code for people to scan that will take you to our next Tech 20. I think, is that on the next slide, Rod? I'm not sure.
I
but there is
think. I tried to put it up, but for some reason it says it's paused. So
having some technical difficulties there, which is.
Are you seeing that?
Oh, there we go. Yeah, leave it at that. That's it should be able to pick up the QR code there. That'll take you to our next Tech 20, which is scheduled for next Friday at 11 a.m. So thank you to Rod. Thank you to our attendees. And that's it. We're done. Have a nice weekend, everybody.
Okay, thank you.